This video is our second kinematics, AP Kinematics video for one-dimensional motion. Recall that kinematics in one dimension is the study of the motion of objects or particles in just a straight line, one-dimensional path without any regard, no care for the forces that are causing that motion to happen. It's important at this point now to mention that all of our study of kinematics is going to be limited to what is referred to as UAM, or uniformly accelerated motion. This means that the acceleration is always constant. If I draw an acceleration time graph, of which I will draw two types today in this video, the line on that graph is always straight. It's not changing. The value of acceleration is not changing. It may change at a different point in time. It may flip immediately and instantaneously to a different acceleration, but it's always a flat line, meaning there's no slope, no non-zero slope of my acceleration. We'll see what that looks like, and that's an important limiting factor for us. Okay, all of the accelerated motions we study in this class this year are going to be uniformly, constantly accelerated. Okay, we have three different types of graphs in this kinematics graphing module. One is of position, that's what the P there stands for. One is of velocity, and one is of acceleration. And these are all always put on the y-axis, and they are versus time on the x-axis. The three graphs I'm about to draw are position, velocity, and acceleration graphs when the acceleration is equal to 0, meaning that the velocity is not changing. Here are my three graphs. I'm going to be sure to label my sides. I'm going to, in this case, just to be clear, write out my quantities on the y-axis, bracket the symbol used to represent them, and in parentheses put the units. So you see position given by x, in its units meters in parentheses, velocity given as v with its units meters per second in parentheses, acceleration given as a with its units meters per second squared in parentheses. Okay, we've seen this graph already, and that's where position versus time is linear. In this case it's increasing. As my example, I'm going in the positive direction, so that's why I'm in my first quadrant of my graphs, but it's totally possible that you could be in the fourth quadrant with a negative position, because we have a change of position is our displacement, and that's a vector quantity. We could be moving in the positive direction, say north, and then we could turn around and move in the negative direction, say south, right? And so we need to be aware that just for this example, I am using the first quadrant to save space. If that's the case, we have that linear function in our position versus time graph, where position is changing at a constant rate, meaning its velocity, the slope, is constant. So what's that look like? The velocity time graph looks like just a zero slope straight line. It's the same velocity the whole time. So whatever that slope value is for the position time graph, that slope value is where my pink line on the velocity time graph is on the y-axis. And acceleration, I said in these three graphs the acceleration is going to be 0, so there's my pink line indicating my function for acceleration versus time. Acceleration is a constant, zero slope, zero value function. Some things we can know immediately. In our position time graph, we can immediately read what I'm going to be writing in black, immediately read off the graph the position of a particle at some given time and its displacement or change in position of the particle if we take 2 points on that line. We can also find the slope, which we said is the velocity, and if we write that out, we see that the slope in green is delta x. That's what's on the y-axis. Remember, your slope is our change in y-axis stuff over change in x-axis stuff. So what's the stuff? What's the quantity that's on those axes? Well, it's delta x, change in position, that's on the y-axis, divided by delta t, the change in what's on the x-axis, time, and that's our velocity. We'll say more about what that velocity is in the next set of graphs too. Okay, we should remember that velocity is a vector, so it could be a positive or negative slope there. In my center graph, I can read directly the velocity at some given time just by looking at my graph and my y-axis, or my function in my y-axis. And I can also quickly calculate my change in velocity from two different points. So if I pick 2 points in time on my velocity time graph, we can see that v is the same. So v minus v naught would be 0. My change in velocity is 0. And indeed, my acceleration is 0, which means that my change in velocity should be 0. No acceleration, no change in velocity. My slope on the velocity time graph is what's on the y-axis over what's on the x-axis, delta v over delta t. And that's my acceleration. And like we just said, you can see that slope is 0, which indicates our acceleration is 0. We can also find the area under this curve, and this has physical significance. Let's look at what I've written on the x-axis. I have two arbitrary selections of time on the x-axis, t sub 3 and t sub 10. In between there I have what I'm calling delta t. So that would be t10 minus t3, whatever those actual second values are. I also have on the y-axis v0 at the y equals 0 location, and v, the final velocity, up somewhere where the purple or pink function is. My area then is the length times the width of this rectangle, which is delta v times delta t. If I write that out, and I can also write the units there to help me, I notice that my t's will cancel out because delta v is equivalent to displacement over time, or delta x over delta t. Those delta t's cancel out, and I'm left with delta x, the displacement. We can also see my units cancel the seconds, and I'm left with meters over 1. So when I find the area under the curve, and the curve can be a straight line or a curve, we just say the curve generally. The area under the curve in a velocity time graph tells me the change in position, or the displacement. Two ways we can see that: by building that rectangle and doing delta t times delta v and seeing how the t's cancel out and I get delta x displacement. Also, the quick way to remember, look at your units on the y and x axis. If I'm finding area, that's a multiplication operation. Multiply my units and I get meters, indicating I'm going to be finding displacement. The acceleration time graph, as we already said, has a zero acceleration. A versus t will only be flat lines, as I mentioned, in uniformly accelerated motion, and just FYI, if there were to be a change in acceleration, that is referred to as jerk. Alright, we have zero slope, there we go, so no change. I can read my value directly, so v is equal to 0. Alright, in this next page, we're going to look at, again, position, velocity, and acceleration versus time graphs, but this is when acceleration is not equal to 0. It could be a positive or negative quantity. Again, I'm going to start this time actually on the right side with acceleration. Same thing as I wrote before. We have these values of that can be read directly: the value of the acceleration, the value of the change in the acceleration, if we have some. And notice we only have flat lines. The purple, or the pink line rather, here is now some positive value of the acceleration. Its slope is still 0 because it's not changing. We have uniform constant acceleration. It just happens in this case, in my example, it's positive instead of 0 like in the last example. I can also find my area here. And the same way I wrote out my diagram of the area on the velocity time graph from the last set of graphs, I can notice that my delta t's will cancel out and I'll be left with the change in velocity. And my units also cancel out to remind me that meters per second are the units I'm left with if I find the area under the acceleration versus time curve. So that area indicates change in velocity. It takes me to the left. Here we are over to the left now with the velocity time graph. Since acceleration is some positive constant value, my velocity is actually increasing at a constant rate. The value of the slope of the velocity time graph is the acceleration. I find that delta v over delta t, my slope, that equals a, and that should be equivalent to the value given on the y-axis of the acceleration versus time graph. I can still see v and delta v directly if I need to measure it. And now I can also find the area under the curve for the velocity time graph. Turns out this is a triangle this time. That 1/2 is a constant. We'll come back to it when we find our first kinematic equation. But you can see that my delta t's will cancel out for my area, and I am left with displacement, or change in position. So again, the area under the curve for the velocity time graph is still the displacement. And that slope, just to write it out, is still delta v over delta t, our acceleration. Now we get a little change. Our position time graph, as we will notice for most of our dot diagram lab activities when we were speeding up, that position time graph was a curve. So I try to draw a curve to the best of my ability to make it quadratic, but that's the type of function we're looking at. I can still read x and delta x, or change in position, by directly looking at my graph. Now this is going to be important. I'm about to draw a secant line, hopefully. No, I'm drawing a tangent line. So ignore the secant writing that's up there. What I'm drawing right now is a tangent line that is the instantaneous velocity. I'm going to go back and ad-lib what my secant line will look like, because this is going to be an important concept for us. If I draw a line, say, from any 2 points along my curve, I can find some slope here. And this secant line is a secant because it's cutting my curve in 2 points. The next line that's going to show up there, as you already started to see, was my tangent line, and that's different. So I can find the slope of my secant line here is still the change in y over change in x, but I'm finding a change in my position divided by some change in time that's going to be equivalent to my average velocity. These are two separate points, and I use that to find my average velocity. My slope here is the change in y, which is my delta x, change in position, over my change in x-axis, which is change in time. All right, so just as before, that's what my slope is indicating, but I'm using 2 points to get that slope value, 2 points to draw that line, and that's the secant, and that's going to be my average velocity. We'll go back to what I had coming up before, and that's my tangent line. Now, if I find the tangent line at a point, then I can find the slope of that tangent line, and at that point, that provides me with the velocity at an instant in time. So when I find the secant, I've cut my curve and found an average velocity between 2 points in time. If I find the tangent line tangent to the curve at some point, then I've found my instantaneous velocity, or the velocity of the object at that exact moment in time. Now I have to use the calculus to do this, so we don't actually do this in this class, but it's important to know that when I find the instantaneous velocity, it is supposed to be at an instant, a very specifically defined moment in time, not a difference in time. And so mathematically that means I'm finding the limit of the change in position with respect to time as the change in time approaches 0. And that becomes the derivative dx by dt, which is instantaneous velocity. We just need to know conceptually the difference between instantaneous velocity and average. Often we write the average velocity as v with a bar over it, and instantaneous velocity just as v. I think that's all we actually have for this video. Indeed it is. So make sure that when we come in, we're able to have these discussions about changing different position, velocity, and acceleration time graphs, and make sure you do practice with the physics classroom interactives and translating from dot diagrams to position versus time, velocity versus time, acceleration versus time, and physical descriptions of the scenarios. That's it.